Morning pre-calc, or maybe it's not morning when you're watching this video, but happy school day to you. We are going to continue our study of polar curves. If you look right here, this is a copy of the notes that you can print out if you like. It's not necessary to print out for today, but it is helpful. These are three different examples of polar curves that have been graphed, and they're really funky curves, and they are polar functions, but you'll notice when you actually graph them, they don't look like functions. They don't pass the vertical line test, and if you graph them on your calculator, you would see them following a pattern that is just really interesting and different. And so our goal over the next couple of days is to begin to sketch some polar curves. If we were actually together in the classroom, we would be doing this in a much more rigorous point-by-point manner. We're going to try to do a little bit of a bird's eye view of polar curves so that you're familiar with them, but it is challenging to do without being together. So one of the things that we're going to look at is some symmetry that these curves experience. But in order to really jump into determining symmetry, there are a few things that we need to recall from just previous study this year. And so you can turn this over if you want to take some notes on that. But one of the things that we need to talk about are odd and even functions, or even and odd functions. We're going to do just a quick little recap. We have talked about this. Remember that even functions. We say that a function is even if when you put in opposite inputs, you get the same output. So we could say f of the opposite of x is equal to f of x. That is the algebraic definition of an even function. Opposite inputs generate equal outputs, the same output. Now, visually, the easiest function to think about, I think, for an even function is y equals x squared. I think of that because the exponent is even. Notice there's some symmetry about the y-axis here. But that means if you put in 3 and negative 3, you would get the same output of 9. And so that is an even function. An odd function, if you recall, means if you put in opposite inputs, you get opposite outputs. So you're putting in x and the opposite of x, and the outputs are the opposite. And the easiest example of that is the power of 3, x to the third, since 3 is odd. That's how I remember that. Our nice cubic function. If you put in 2, you get an output of 8. If you put in the opposite, negative 2, you get the opposite output of negative 8. That's negative 8. This is 8. And so opposite inputs generate opposite outputs. And there's some symmetry there. That's a reflection about the origin. So that's odd and even functions. Now, what does that have to do with polars? Well, we need to come through the element of our trig functions first. So one thing I know that I don't believe we mentioned this when we were studying trig functions, but the cosine function begins at that maximum. Notice the cosine function is symmetric about that y-axis. This is an even function. Opposite inputs give you the same output, and you see that symmetry. So we can say that the cosine of the opposite of x will give you the same thing as the cosine of x. That is a trigonometric identity. For sine, here's the sine function. I'm not putting in the scaling, but you get that. Sine is an odd function because the opposite inputs give you opposite outputs. It's symmetric about the origin. So we can say that the sine of the opposite of x is equal to the opposite of sine of x. Now, these we call our odd and even trig identities, and we're going to be using these two today. There are also the sum and difference formulas for cosine and sine that we will also be recalling today. Remember that the cosine of A plus B, that is equal to the cosine of A times the cosine of B minus the sine of A times the sine of B. Do you remember that one? You'll just want to write that down and have that handy. Also, the cosine of A minus B, that's equal to the cosine of A, cosine of B, plus sine of A, sine of B. And the same thing, we're also going to need our sum and difference identities for sine. Remember, that is the sine of the first angle, cosine of the second angle, and then plus on the sine's the same, plus sine of the second angle, cosine of the first angle. And remember that if you change that to the difference, just the sign changes. So sine A cosine B minus sine B cosine A. And so these are our trig identities that we're going to be putting into use in polar form. So you're just going to want to keep those handy. I'm going to flip that around. Now, let's come back to these polar curves. Now notice we've got some symmetry in each of these. It's a different type of symmetry. Here, in this first one, we have a graph that is symmetric about this line, and we don't want to call it the y-axis because we're not graphing in rectangular xy coordinates. We would call it the line theta equals pi over 2 because that would be the angle of rotation, and that line right there is that theta equals pi over 2. And so we have that symmetry there. Notice a point over here. Let's call this point r theta. That can be reflected over here, and we have this point. It is symmetric, reflection across, and we would call this point still the same r value, still same distance, but instead of that angle of theta, we're theta less than pi, so we can call this point pi minus theta. That's that point right there. But we could also think about that point with a negative r value. That would also be negative r, so coming from this direction, and theta down here, negative theta. Because if you go here, I went up theta. If I go down theta, and then the r value going negative, it would send it across to there. So that's two different ways to identify that point. And that actually is going to provide us these 2 points with our symmetry test. So when we want to test to see if something is symmetric to the line theta equals pi over 2, instead of in our equation having r theta, we're going to replace it with either this point or that point. And if we can manipulate that equation and have it turn back into its original form, it will be symmetric to the line theta equals pi over 2. So I'm going to replace r theta with either negative r, negative theta, and I list that one first because that one's the easiest one to take care of. And the second one, or r theta, pi minus theta. And we're going to work through some examples as to how we actually do that. But that's where those 2 points come from. Then notice here we've got a nice graph with petals, and it's flower looking, and it's got this rotational symmetry, but that's not the symmetry we actually want to look at here. We're actually looking at the fact that it's symmetric to the polar axis. So the horizontal axis, we can see that a point up here is reflected down to a point down there. And same thing over here. Up here would reflect down there. It is symmetric to the polar axis. So if this is the point r theta, and I reflect it down, we would call this r negative theta. But we could also refer to it in terms of a negative r, and then it would be over here, the negative bringing it back, and so the angle would be pi minus theta. 2 ways to describe that point. So that's going to provide us the points that we're going to use for our polar axis test. We would replace r theta with r negative theta, or negative r pi minus theta. Okay. And then we have the last bit of symmetry, which is that rotational symmetry, a point here, r theta. It reflects around 180 degrees or pi radians to over here. So it is a rotational piece, symmetric to the pole, and it moves pi radians away, or 180 degrees away, but I'm dealing with things in radians, so I'm going to call this theta plus pi radians. And then if I think of the negative r value, that would be the same angle, just going the opposite direction. So negative r theta. So those are the 2 pieces I'm going to use for my pole symmetry. I'm going to replace it either with negative r theta or r pi plus theta. All right? So now when I look at these, what am I doing with these pieces? We are going to take an equation like r equals 2 plus 2 cosine theta. I want to test if I graphed that, if I actually generated a table of points, which would take quite a bit of time, would I have a graph that's symmetric to the line theta equals pi over 2, symmetric to the polar axis, or symmetric to the pole? And so I'm going to test those by plugging in each of these points. Instead of r and theta, I'm going to replace r with negative r and replace theta with negative theta. And then I'm going to use those trig identities to see if I can manipulate it back to this form. It's like a trig identity, verifying an identity. And if I can do that, then it passes the symmetry test. Now, why did I list these ones first? Because they don't have an addition or subtraction sign in them. So these are going to be much easier to test. If I get a yes on any of these, I do not have to test the second one. If it passes the first one, it's a yes. But if it doesn't pass the first one, it still could pass according to this point. So if I get a no on the first point, I'm going to plug in the second point. So let's just hop on in and see if we can figure out how to do that. All right. So I'm going to test for theta equals pi over 2 symmetry. So I'm going to replace the r with negative r in this equation. My equation is r equals 2 plus 2 cosine theta. So I'm going to replace r with negative r. And then I have 2 plus 2 times the cosine of theta. But instead of theta, I'm going to put negative theta. All right. Now this is where I use those trig identities we started off with, the odd and the even. Because notice we have the cosine of negative theta. Well, cosine is an even function. So if you put in the opposite angle, you're still going to get the same output as cosine of theta. So I can just call this 2 plus 2 cosine of theta. Because cosine is even, opposite inputs give you the same results. Now I want to solve for r. So I'm going to divide everything by negative 1, and I end up with r equals negative 2 minus 2 cosine theta. Solving for r again. Do I get the same equation? No. This is a big no. So it did not pass. But I do still need to check this point to see if it passes. So let's plug in positive r, and instead of theta, pi minus theta. So r equals 2 plus 2 cosine of pi minus theta. Well, now I've got some trig identity for the difference of two angles in cosine. So I need to do some expansion. This becomes 2 times the quantity. I want to keep that in front of the parentheses. Cosine of the first angle, cosine of the second angle, plus sine of the first angle, sine of the second angle. So now I need to simplify this. And at first it doesn't seem like it's simplified, but I know what the cosine of pi is. The cosine of pi is negative 1. So this becomes negative 1 cosine theta. And then I also know what the sine of pi is. The sine of pi is 0. And 0 times sine of theta is just 0. So then if I simplify even further, I have r equals 2. And I'm going to distribute that 2, so it's minus 2 cosine theta. Well, is that the same equation? Nope. So there is no symmetry across the line. Theta equals pi over 2. So I'm going to move to the next one. And you can have more than one symmetry. So you need to take care there. And you do need to test all of them. So next we're going to test the polar axis. And so I'm going to put in r and negative theta. And so r equals 2 plus 2 cosine of negative theta. But this again, this is an even function. So if you put in the opposite, it is the same as the original. And do I get the same function? Yes, in fact, I do. R equals 2 plus 2 cosine of theta. So yes, it is symmetric about the polar axis. And because I got a yes here, I do not need to check the other one. I already know it is symmetric. So I'm going to mark down here that it is symmetric about the across the polar axis. Now, I can have more than one of these, so I still need to check that last one. And I'm going to check across the pole. And so negative r equals 2 plus 2 cosine of theta. And I can see if I divide both sides by -1, this is not going to work. That's a no. Not the same. Maybe it'll work when I put in r and pi plus theta. So let's try that. Let's do r, and we have 2 plus 2 cosine of pi plus theta. And now I'm going to expand that with my trig identity. So times the quantity cosine of pi, cosine of theta, minus sine of pi, sine of theta. And we already figured out what cosine and sine were, so it's very similar up here, except the sign is different. So this becomes, this was a 0. So 2 times, and this is a, what is that, -1. So then r equals 2, whoops, if I distribute that, I get a minus 2 cosine theta. Not the same thing as what we started with. So it's a no there as well. So we only have one type of symmetry according to our symmetry tests. Now, important to note over here, passing a test confirms symmetry. So we definitely know that this function right here is symmetric across the polar axis. But failing a test does not exclude symmetry. So we need, we could try other tests. It doesn't mean that you failed here, that there is no symmetry. So we have to be careful there. All right, I would like to try 2 more examples, just so that you see a variety of pieces. And I know this is a longer video, but we're getting into some more complex things. Let's look at this function here, because this function has a sine function in it. And so when we test, we're going to be utilizing our odd function properties here, because sine is an odd function. All right, if we're going to test this, we're going to put in, and you might want to have the first side handy, we're going to put in the ordered pair negative r comma negative theta. So negative r equals 1 minus 4 sine of 4, and then negative theta. Now, sine is is an odd function. So opposite inputs generate opposite outputs. So it's like I can pull this negative out, and it's going to make this subtraction into addition. So this is the same thing. And you might be like, oh, look, we're close. But when we actually divide both sides by -1, it makes this 1 negative, and then minus 4 sine of 4 theta. So that actually didn't work. It did not pass because we did not get the same thing. So we're going to try the other point. We're going to put in r and pi minus theta. So 1 minus 4 sine of 4 times the quantity pi minus theta. Now here we need to do a little distributing first. 1 minus 4 sine of 4 pi minus 4 theta. So we have to distribute that 4 first before we apply our difference formula for sine. And when we apply that, that 4 in front is the coefficient, so put some parentheses there. And this would be sine of the first angle times cosine of the second angle minus sine of the second angle times cosine of the first angle. All right. And think of your unit circle. We know where 4 pi is. It's going around twice. There's 2 pi. So 4 pi, we're looking right there. The sign of 4 pi is 0. So this whole piece goes to 0, right? Because 0 times anything is 0. And then we are going to subtract off sine of 4 theta times the cosine of 4 pi. The cosine of 4 pi is 1. This goes to 1. So this piece is just sine of 4 theta. And then our negatives, when we multiply those, we get 1 plus 4 sine of 4 theta. Now, that's a lot of good work, but unfortunately, it is not what we wanted. So it did not pass that test. All right, so we're going to move on to the next test to see if it passes symmetry across the polar axis. And for that, we're going to plug in an r and a negative theta. Now, again, we have an odd function. So the sine of the opposite of theta is equal to the sine of the opposite of sine of theta. So that negative comes out, and it's 1 plus 4 sine of 4 theta. But again, not what we started with, so this is not passing the symmetry test. And we'll try the next point. And it's a bit of work. You're only going to have 4 questions for homework. So it will give you enough to get you some practice and a variety, but not hopefully exhaust you. For the second piece, we're putting in a negative theta and pi minus theta. Now, do note, we are ready. The only difference between this one and the top one is that the r is negative. We've already done all of this work. So you can do it again if you want, but this side right here actually simplifies, all of this simplifies to 1 plus 4 sine 4 theta. So I would just say, hey, according to what's above that, right-hand side equals 1 plus 4 sine of 4 theta. If you've already shown the work somewhere, you don't have to show it again. And then I can apply that negative 1, and I get negative 1 minus 4 sine of 4 theta. That is not what we wanted, so it does not pass the test. All right, we've got one more left, the pole. And putting in the negative r and the positive theta. That one I like the best because you're just really making everything the opposite. And nope, that doesn't pass it. So let's try the last one. See if there might not be any symmetry at all. 1 minus, we're putting in r and theta, pi plus theta. So 4 sine of 4 times, you can do theta plus pi or pi plus theta. And that is equal to 1 minus 4 sine of 4 pi plus 4 theta. And I'm running out of room. I should have written smaller. So this is sine, cosine, plus sine of 4 theta, times cosine of 4 pi. All right. 1 minus 4. Let's see. The sine of 4 pi was 0. The cosine of 4 pi was 1, so this just becomes sine of 4 theta. And look at that. It is, in fact, what we started with. So finally, we found one. It is symmetric to the pole. Okay, one last example. I just want to show you this one here because it's really interesting. We have an r squared. We'll be looking at those. Those provide a different type of graph as well, but it's the same test. Watch what happens as we look at, is it symmetric across that vertical axis? I'm going to put in a negative r and a negative theta. Now, when you square negative r, that just gives you r squared. And cosine happens to be an even function, so I can replace cosine of 2 of negative theta just by cosine of 2 theta. And so, yes, that is symmetric across that line. How about the polar axis? Polar axis, we're using just the regular r and a negative theta. And because cosine is even, you get the same output with opposite inputs. And so look at there. We're back to r squared equals 9 cosine of 2 theta. So that one is also symmetric across the polar axis. Mark that one off. How about this last one, the pole? Put in a negative r and a positive theta. Well, negative r squared is just r squared. And it is also symmetric about that pole. This graph happens to have all 3 types of symmetry. Why are we looking at symmetry? Because it's going to help us sketch these graphs. It's going to give us an indication of what symmetry we will see, and it will also limit us in terms of how many points we have to look for. If we know that symmetry exists, we only have to graph certain quadrants, and then we can do that reflecting or that rotating. And so I hope that you have a sense of what these 3 tests look like. You'll get a chance to practice those in the homework, and thanks for sticking in there for a long video.